Okay, so at this point in our AP statistics course, you have some pretty valuable skills. Really, you think about it, you're able to take data and get it organized and summarized numerically and graphically. Think about one variable data. You understand the difference between what something like a median is explaining to you as opposed to the mean. And you could also look at a graph of the distribution of the data to see how the shape of the distribution could affect those different measures. You also understand measures of spread, like standard deviation, like interquartile range, and what those values tell us. Then what we also did in chapter 2 was look at individual measures in a set of data. What does a z-score mean? What does a percentile mean? Okay, all these are really, really important in terms of summarizing and explaining what, basically what a set of data is going to tell us. And then in chapter 3, a really powerful tool for a statistician, we looked at correlation and understanding the difference between correlation and causation, and also linear regression, and how that the tool that gives us to make predictions with one variable based on another. So what we're going to do now in chapter 4 is kind of double back and try to think about how is this data collected. If we have data that shows a strong positive correlation between two variables, how do we go about collecting that? Was it collected responsibly, or was it done in sort of a biased way? I pointed out some books to you earlier this year. How to Lie with Statistics is a great one. But if people want to, if people understand statistics, they can take those numbers and manipulate them to really paint a picture or tell whatever story they want to tell. But if we're intelligent statisticians, we can dig a little bit deeper and look and see, how was this data collected? What story is it really telling us? Is it able to tell us a story that we want? So what chapter 4 is going to be all about is the difference between, first of all, observational studies and experiments. The experiment is much more powerful tool for the statistician, and those of you that have dive deep into science fields would agree with that. In order to really make advancements in science, we need experiments. We need to control for variables. It's a lot of work. It's a lot of heavy lifting. So we're going to take a look at that in depth. What does that mean to have an observational study? Maybe we just send out surveys and ask people's opinions. And what's the difference between that and when we set up an experiment? So we're going to find that there are many different ways to collect data, and depending on what question we're trying to answer, one method may be preferred over another. So I want to jump to a graphic that I posted in Schoology that I feel like is, if you can print this out, put this in your notebook, put it in your Frappy notebook, this might be one of the most valuable graphics that we get this entire school year. So what we have in this graphic, and I collected this, I think the very first year that I was teaching AP Statistics, I went to a workshop, and this graphic was given to me in a handout, I guess in electronic form now too, because I have a PDF of it, unless I made this myself. But it breaks down the different ways, at least a few different ways that data could be collected, basically in terms of observational studies. If we were doing a survey, we're trying to ask people's opinions. Sort of the gold standard is this first one, the simple random sample. If I would like to get a sample that's going to be representative of the whole population, what I want to do is basically number the whole entire population. If there's 1,000 people in my whole population, or 1,000 items, I want to number them 1 through 1,000. Then I'm going to have some kind of random element. It might be a random digits table, which I'll show you that your textbook has that. You can look up a random digits table on the internet. Some kind of random element that is going to randomly select items from the population or people from the population that are going to be included in our sample. That's our simple random sample, when everyone in the population has the same chance of being selected. And if we want a sample of size 50, then any particular sample of size 50 has the same chance of being selected, if that makes sense. Stratified is a little bit different, but I'll try to give you an example of where this might have a purpose. Suppose we wanted to do a survey about who would attend a homecoming ceremony. Well, we might expect that freshmen and sophomores and juniors and seniors might respond differently to that situation. So maybe we go into the population first and foremost, and we divide them up into strata, which would be groups that have similar characteristics to each other. and our strata there in that example I gave you would be freshmen, sophomores, juniors, and seniors. Then what I do is I take a simple random sample of freshmen, and then another simple random sample of sophomores, and another simple random sample of juniors, and then finally a simple random sample of seniors. So I take several different simple random samples. Now, the stratified random sample, I'm going to slide down to the bottom. This one most often gets confused with what's called a cluster sample. So I want to differentiate between these two. The cluster sample would be different this way. If we divided the population into freshmen, sophomore, junior, seniors, then what I would do is I would randomly select two of those, or three of those. I would randomly select the freshmen and randomly select the seniors. And then I would sample everyone. So hopefully you see the difference between that. Instead of having 4 different samples, I would only take a couple of clusters, but then I would get everyone in the cluster. Freshman, sophomore, junior, senior, probably not a great example of that. Maybe better idea would be, let's label all the elementary schools in the district, 1 through 6 or 7, however many there are. We put all those names in a hat, in a bowl, on a piece of paper, and I randomly select 3 of them. And then I pull out those 3 and I see I have Birches, I have Bells, and I have Whitman. Well, I'm going to go to all 3 of those schools and I'm going to sample everyone in those schools. So we kind of take a census of the clusters that get selected. Systematic just works in a way where this is, every 5th person, that comes through the checkout line at a grocery store, we maybe sample them, right? It's every, and what we do is we randomly select that number. So the number 3, every 3rd person, or every 5th person, or every 6th person, that number is generated at random, but then we just go systematically. So if the 4th person gets surveyed, then the 8th person gets surveyed, and then the 12th, and so on. All right, so let's see if we can unpack some of these in some examples. So the first thing we want to talk about is whether or not our sample that we have, that we already know how to analyze and summarize, is representative of the population that we are interested in. Okay, so one of the issues with the last presidential election was that it seemed like the predictions were wrong. And the pollsters are very good, and the statisticians who work on that are very good at summarizing and organizing the data, and they also understand probability really well. So it was very confusing as to how the results of the last election were predicted incorrectly. So here's a former president of ours, Harry Truman, holding up a newspaper, the Chicago Daily Tribune, very famous. You've probably seen this in your history classes, that clearly says Dewey defeats Truman. And this was published, the newspapers were printed. A lot of times they do this with Super Bowl t-shirts. They print, the Patriots are going to win the Super Bowl, and then the Eagles beat them in the Super Bowl. So those t-shirts have to go somewhere. They send them off to people that, need a t-shirt to wear. But this is very, very famous. Dewey has a copy of this because, the pollsters were so confident in their prediction of the election that Truman was going to lose, and he ended up winning. And the issue there was very easily explained. What happened in that situation was that those polls were conducted by the telephone, and at that particular time in history, only people that had a little bit more money than other folks, were able to have a telephone. So if only people who had telephones voted in the election, then Dewey probably would have won by a landslide. But the fact was that many people who didn't have telephones voted, and disproportionately they voted for Harry Truman, so he ends up winning the election. Well, in the last election, as best as I've been able to ascertain through research and listening to what came back, you had a popular vote that was, it swayed in one direction entirely, but it's the Electoral College that elects our president. So in a lot of these situations, especially in Pennsylvania, that was a big part of that. When people were surveying or asking people their opinions on who they were going to vote, and they were trying to predict the election, people just weren't truthful. They didn't tell the truth. We call that bias. Okay, when there's bias in the sampling, and that particular type of bias is called when somebody lies. When somebody says, "Well, I'm going to do such and such," and they don't, we call that response bias. It's very, very difficult for a statistician to deal with that. I mean, we do our best. Suppose I wanted to survey high school students about underage drinking. It probably wouldn't be a great idea to have a police officer come into my classroom and say, "Raise your hand if you drink on the weekends." It's not, I'm asking, basically in that situation, I should be expecting that people probably won't be forthright and truthful. what I might do get a better sample there would be to make something anonymous, so people feel a little bit more comfortable telling the truth about that situation. But for whatever reason, in the last election, presidential election rather, when people were going to the polls or being surveyed, they just didn't tell the truth, and maybe they changed their mind at the last minute. Who knows why? There's many theories, but somehow the pollsters got that one wrong, and it's their job to kind of get that right. They don't want to make those kinds of mistakes, like for the statisticians who incorrectly predicted Harry Truman's loss. That's embarrassing for them. That's their job to make those predictions correct. They don't want to make those types of mistakes. So let's look at what we have here. You have the student government at a high school surveys 100 students. Okay, so that's going to be our sample. All right, that's definitely our sample. It's the 100 students that they select to get their opinions about the change of the bell schedule. So what we're looking to identify here is the population of interest. So the population in that situation should be all students at that school. Okay, that's definitely our population of interest. And then the sample is the 100 students that they surveyed. Okay. So in part B, we have a quality control manager at a bottling company selects a random sample of 10 cans. Okay, so that's definitely going to be our sample from the production line every hour. Okay, so he does this every hour. So our population is going to be all cans produced in an hour. Okay, and then the sample would be the 10 cans that we selected. So what we're hoping for in all of these situations is that our sample is representative of our whole population. In the case of Dewey defeats Truman, and in the case of our last presidential election, the samples that were gathered to make predictions, the math was fine. There was nothing wrong with those statisticians' ability to organize and summarize the data and also understand probability and random chance. All of that was very, very sound. Where both of those situations went sideways was in their sampling. So we want to be really, really careful about that. Okay, so if we can think about the graphic that I showed you to start here, see if we can apply that. If not, we'll see what's happening in this situation. In May 2010, the Los Angeles City Council voted to ban most travel and contracts with the state of Arizona to protest Arizona's new immigration enforcement law. The Los Angeles Times conducted an online poll, so I'm going to lock in on that, and asked whether the city council was right to pass a boycott of Arizona. So that's a very simple question. Was this right or not right? The results showed that 96%, that's a pretty big number, of the 41,068 people in the sample said no. What type of sample did the Times use in this poll? Explain how this sampling method could lead to bias in the poll results. So let's think about this. So there's a couple of issues here. We have one of the biases that we'll find and that we see here. This is called, since this was an online poll, this would be what we would call a voluntary response bias. You could also call this a response bias where, well, not response bias rather, but a selection bias. We would call this undercoverage. In other words, first of all, only people that have access to being online would be included in this. Now, in 2010, I guess we could suppose that many people are online. But if you're not online and you could still vote, or you still have an opinion that matters, you're being systematically excluded. Okay, so this is called undercoverage bias. But the biggest part of this here is that this would be a response bias, and we call this a voluntary response bias. And what happens in this situation is that more than likely the people that feel really strongly about this issue are the ones that are going to be most likely to respond. And this is sort of a dead giveaway to that. When we get a result like 96%, that's really, really high. So it's likely that people that feel really strongly about this are the ones responding. Whereas there may be many other opinions that differ from that, but they just don't feel as passionate about it and they don't respond. So the result here would be what type of bias is used. This is voluntary response bias. Explain how this could lead to bias in the poll results, right? 96% is probably higher than the actual proportion. Than what we would call the true proportion. Okay, so that 96% number is probably higher than the true proportion of voters who would be against the boycott. It's people who feel really strongly about it, they're more likely to respond. We call that voluntary response bias. It's something that we want to pay attention to it. Undercoverage happens, and you could also cite this as undercoverage. If you said to me, look, Mr. Dempsey, not everybody's able to even respond to the online poll because they don't have access to the internet or they're not online. In that situation, then, we wouldn't call that voluntary response bias. We would call it undercoverage bias, just like Dewey and Truman. The Dewey-Truman situation was people that didn't have phones still were going to vote. So there's a difference. These get confused very easily sometimes, so we have to read carefully. And if you think it's one versus the other, just explain your reasoning. If you said that this was undercoverage bias rather than voluntary response, you need to explain with a sentence or two to me that it's because not everybody would have access to the online poll, and that would be completely acceptable. So the random digits table, we see this occasionally. The first thing I want to point out to you is that these digits here are not random. A lot of times I'll have students look at those numbers and use them in their result. They're not random. They're sequential. 101, 102, 103. Those are the numbering of the lines. So try not to pay too much attention to those unless I say look at line 107. But what I want to lock in on here is that I have 21 stores and they want to survey 3 of them. This is the most important part. Okay, so my stores, the very first thing I have to do is number the stores. And how should I do this given this random numbers table, right? The way I would do that is I would number them 0, 1, or 0, 0. Either one of these would be fine, right? So I have my stores, and one of the stores, if it's the Gap, it's going to get the number 00, right? That's the Gap, okay? And then GameStop is going to get the number 01, okay? And then American Eagle is going to get the number 02. I'm just going to I have to number all the stores in some way or another, okay? So all 21 stores get a number. Then what I do, based on how I number them, and in both of these situations, I used 2-digit groupings. So it really doesn't matter. The most important thing is figuring out what's my population size. If my population size is 100, then I could number them 00 to 99. You see how I don't waste any numbers that way? If I numbered them 001 to 100, that's probably not a great way or an efficient way to look at my random digits table, because when I look at 3 digits at a time, which I'll try to lock in on up here, if we go for 3 digits at a time, you'll notice that it's not likely that I'm getting any 3 digits that live in this region. In fact, I'm going to have to ignore 90% of them, right? Most of the digits are going to be 101 to 999. And then I've lost my opportunity to number them that way. So for us, in our situation with just 21 stores, the best way for us to think of these numbers would be 00 through 20 or 01 through 21. So I'm going to come back up to the number table here, and I'm only going to observe 2 digits at a time. Now, some of you are going to get this right away. This is going to make sense to you right away. Others, you need to see this a few times, right? So as I partition this random digits table, 2 digits at a time, okay? Try to unpack. Now, so I have 3 here and then 9, so that's 2 digits at a time still. I'll keep coming through here. 2 digits at a time, and so on. So let's observe the first couple of numbers. We said we numbered the stores. Let's go with 01 to 21. I think that makes more sense to people most of the time. So if I number them 01 through 21, then the first number that I observe is store number 19. So if store number 19 is Old Navy, then that store is going to get selected. Then the next store I see is 22. Well, 22 is not a digit in our 0, 1 through 21, so it doesn't mean anything to us. Same with 39, doesn't mean anything to us. Okay, 39 does not mean anything. Also, 50 does not mean anything. 34 does not mean anything. Then I come here and I see 0, 5. That would be a store. Okay, so that's a store in the mall. 0, 5. And then I see 75. Doesn't mean anything. 62 doesn't mean anything. 87 doesn't mean anything. But then finally I observe store number 13. So that's how we systematically go through a random digits table to select a random sample. So what we would do next then is go back and see what was store number 19. Okay, whatever store 19 was, that's going to be in our sample. Whatever store 0, 5 was, that's in our sample. And whatever store 1, 3 was is also included in our sample. And sure enough, I did not look further down to see that. But for sure, our stores are listed down below here. We can see them here. We have 0, 5, 1, 3 was selected, and 19, right? We have Carter's for Kids, Mrs. Fields, and Star Jewelers would be included in our sample. So one of the hard things with the quarantine situation is not being able to do a lot of these activities live, which I feel like especially in this particular chapter, we have a lot of activities we can do that lend themselves to being together in a classroom. But we'll do the best we can here. So we'll try to wrap our heads around this situation with the school librarian. There's 20,000 books. What are they trying to estimate? The average number of pages in all books. That's what we want to lock in on in the library, right? So if we randomly grab a book, what's the average number of pages in the book? What's the best way to try to figure that out, right? Now, as they say in the next line here, the library has 20,000 books. So we could just randomly select 50 of the 20,000, or we could think about how fiction books might differ from history books and biography books and so on, right? But in the end, we want a total of 500 books. We're going to take a random sample of 500 books total. And then they also tell us that each shelf has 50 books on it. Okay, so we'll think about that as well. So a couple different ways that we could sample these books, right? First one would be, how do we get a simple random sample of 500 books? Well, we just number all the books from 1 to 20,000. Now, if we had to use a random digits table, we might think about saying that we would number these 0, 0, 0, 0, 1, right? Might need less zeros than that. Yeah, there's really no need to conserve digits here. So 0, 0, 0, 1 to 20,000 if we needed a random digits table. But if we just use our calculator, and your calculator has a feature on it, the random integer calculator, rand int, I'll show you where that is. So if we use our math button here underneath alpha, second alpha, and then test, we hit math, and then we go over to probability, you will see the number 5 random integer situation. If we say, look, we want to pick a number between 1, and 20,000, and we want 500 of them. Now, what can happen here is that we might get some repeats. We'd have to scroll through this list, and we might have to press enter again. If I get repeats, it's going to generate a list of 500 numbers. Hopefully I didn't break my calculator. Looks like he's taking a while. There we go. So these would be the books that I would select. Book number 18,872, 18,167, 2,934, and so on. Now, what may very well happen is we'll get repeats, and we'll just have to simply ignore them and then press enter again, execute the command until we get 500 numbers that are all different from each other. So we could do random integer 1, 20,000. Okay, 500. Until we have 500 different numbers. And those 500 different numbers will represent the 500 books that we are going to select. So you want to make sure you write that in your response as well. The 500 numbers correspond to, there should be some kind of correspondence there. 500 numbers that we select correspond to the 500 books that we're going to sample. Okay. Now, what would happen if we did a stratified sample of the books? Okay. Well, to me, the obvious strata would be fiction, biography, history, and so on, right? So the strata would be the genre of the book. Now, we have to figure out how many genres there are. They don't really tell me. They listed 3 and said so on. So let's suppose there's 10 genres. Okay? If we have 10 genres of books, then we take an SRS, a sample of 50 from each genre. And I don't need to go back into the detail of how I'll get the SRS. How would I get the SRS? I'll number all the books in each genre, 1 to however many there are, and then I randomly select 50 from each book. Now, it's very possible, if you think about it, that maybe there's a lot more fiction books than there are biographies, right? Suppose that 50% of all the books are fiction, and only 10% are biography. Well, then I probably don't want to take, I probably don't want to just divide 500 by 10. I would want to take the 500, I would take a portion of that. So if 10% of the collection is biography, then I would only do 50, I would only want 50 of those books to be biographies, right? If half the collection is fiction, then I'd want 250 of the books to be from fiction. And I would sample accordingly. I would make a percentage breakdown based on the actual breakdown of the population. That's the idea with a stratified sample. Okay, so then the last part asks about how we would do a cluster sample, right? Well, it seems to me like the obvious cluster up here, at least that they tried to explain to me. Sorry, I didn't mean to scribble all over that. The obvious cluster would be 50 books per shelf, right? So if each shelf would be a cluster, okay, then we would number all the shelves. Let's say, well, since they each hold 50 books, so 20,000 divided by 50 is 400 if I did that right. So I would number the shelves 1 to 400. There must be 400 shelves, okay? And then we randomly select ten numbers between 1 and 400. How do I do that? Random integer. 1, comma 400, comma 10. Okay, that gives me my 10 shelves. All right. And then we sample every book. On those 10 shelves. Okay.